Hello everyone. So today we're going to continue on 6.4. So last video we get to look at an example on how to find the absolute maximum, absolute minimum of a real value several variable function. And we realize that when we're doing that, we basically applying what we call the extreme value theorem for multivariable calculus, which is kind of the extension of the extreme value theorem from BC calculus. And we try to do it the same exact way, which is to basically find critical points and then test endpoints and then form a table and then compare the value. The only difference here is that when we're dealing with multivariable calculus, multivariable function, we don't have endpoints anymore, but we instead have a boundary, and therefore we have to somehow find the boundary critical points, and that is what is new in doing this type of question. And so that's what we're going to focus on. But before we actually talk about how to do that, let's kind of summarize how this works. So this example basically demonstrate the general method, which is basically using theorem 6.4.1, general method to find the absolute maximum or minimum for a function f that maps from Rn to R over a region S. So the method would be follow. Number one, kind of like the first step, what we need to do is to identify interior critical points. Now, I do want to point out that some cases, in some of these questions, there might not be an interior of the regions asked for you to find interior critical points. So in that case, you actually don't have to do step one. Now, then how would you know that you don't have an interior critical point to work with? It's really based on reading the problem. So if the problem describes some kind of interior, obviously then you would have to find the interior critical points. Like as in this particular problem, the question specified that we are talking about the boundary and the interior of the equation x squared plus y squared plus 2y squared equal to 1. Now, the question did not mention anything about interior, and also more importantly, when they define the region using equation, they are not using inequality, but equation. Then it's very likely that you're not dealing with interior. Okay, if the question only simply defining the region using equation and without any mention of interior, then you probably don't have interior critical point to work with. But if the question defined the region using equation but mentioned that we want the interior also, then obviously then you have to do this first step. So how do you actually identify interior critical points? Well, we'll be using this. We'll be using theorems 6.4.2, if I remember correctly. 6.4.2. And what does that mean? Well, simply just mean that 6.4.2, which mean gradient of f of x sub 0 equal to vector 0. So you basically try to find vector x sub 0 that will satisfy this equation. Now, important to understand is that just simply identify critical points. We actually don't know if those points will result in maximum minimum. Okay? As a matter of fact, they are candidate for absolute max and absolute min, but they don't necessarily have to be relative max or relative min. And later on, we will talk about how to actually identify that. So, 2, identify boundary critical points. So, make sure you understand that boundary critical points are different than interior critical points. Boundary critical point does not have to satisfy gradient of vector x equal to 0. So important to understand that is that boundary critical points do not have to satisfy gradient f of x sub 0 equal to vector 0. So therefore, you cannot use theorem 6.4.2 to actually find the boundary critical point, which is why it's difficult, because if we can use the same theorem, then we won't separate them into two different steps, because you'll find all of them in one step. So how do you find boundary critical point? One way to do that, one method, is to parameterize the boundary and then form a composition. And this way will allow us to form a function that we can form the derivative of and then find the critical point like we normally would do. Because once you've parameterized the boundary and form a composition, then now you can identify a boundary by using the derivative. Now, however, this is not a good method because of the fact that you have to parameterize the boundary, which is actually extremely difficult to do. In our previous example, it was easy because we have an ellipse, which is a very easy way to parameterize a curve. That's very easy to parameterize it because we know how to parameterize circle. But if it's something else, we might not know how to do that. So therefore, the remaining of the next topic will be talk about a method to actually do that. And that will be this method, which I'm going to name, but we'll talk more about it and we'll define it once we finish here. Another method is called the Lagrange multiplier method. So that's what we're going to talk about in today's video as well as tomorrow's video. And finally, once you identify all the critical points, then what you simply going to do is use a table to compare the function values. That means the output of each critical point or each points from step 1 and 2 to determine absolute max and absolute min. So as I said, the most difficult part will be step 2. So let's talk about what is this thing called Lagrange multiplier method. So Lagrange multiplier method is basically used, allow us to actually find the boundary critical points, provided that we're given the constraint to work with. And actually allow us to work with no matter how many different constraints we have. So instead of having one equation to define the boundary of the restricted domain, this could actually be used for multiple equations. However, it is not an easy method to do, so it's definitely something that will require you to practice a lot to make sure you can do it right. So here's the theorems, 6.4.3, which is referred to as Lagrange multiplier method. Sometimes I just call it LMM, you know, for short. So here's what the Lagrange multiplier method states. It states the following. Let's say given a differentiable function f that meant from Rn to R. So this is the function that we try to optimize. Let's say f has a set of n constraint. So the constraint would basically meaning that these are things that restrict the domain of the function. And these constraints are given by a set of function g, which I'm going to call g sub 1, g sub 2, all the way to g sub n. So notice that these set of function, note that each g sub k of vector x is equal to z sub k. And what does that mean is that these are basically level set for the function g sub k, which also map from Rn to R. So it's extremely important to understand that the constraint must have the same number of variables as f. Otherwise, you really can't define the constraint. You're not defining the constraint correctly. And the only difference between the constraint and the function f is that function f has a variable output because we don't know what the output of f is. In fact, that's what we've tried to figure it out, is the max and mean of f. The constraint, on the other hand, must have a fixed output value. That's the reason why they're constrained, because they are fixed as what they equal to. So this is what the Lagrange multiplier basically say. If f has an extreme value, so here meaning maximum or minimum value, at some x sub 0 point, subject to the given constraint. So if you want to, you can go ahead and write that down. That basically just means boundary critical points or boundary maximum minimum. Then there exists a set of scalar lambda 1, lambda 2, dot, 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 to lambda n, such that this is true. Such that the gradient of f at x sub 0 is equal to lambda 1 gradient of g at x sub 0 plus lambda 2 gradient of g2 x sub 0, yep, that's g1 on the lambda 1, plus dot 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 plus lambda n gradient of g of n at x sub 0. Oh, actually, you know what? Alright, I'm going to have to fix this. Okay. The problem, because I say function f that map from Rn to R, but I don't want you to confuse at the n with the n constraint. So I'm going to actually fix this n to k. You know what? Actually, I'm going to call that m. So that way it's easier. Okay, so this is m. Oop. And so I'm going to go and change this to a m. And I'm going to change these two to m. There you go. Much better. And this set of scalar constant, maybe I would say, this set of constant, lambda 1, lambda 2, dot, 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 to lambda m, they are basically what we call Lagrange multiplier. So it's not easy to understand how this theorem works, so let's go over it quickly. So if you give a function f that maps from Rn to R, so that's basically a real value several variable function. We need to know that this function is differentiable because we need to know that the gradient exists. And let's say this function have m constraints that restrict its domain. And these constraints are given by a set of equations that has a fixed output value, which I'm going to collectively call them G. So therefore G1, G2 to Gm. It could be 1, it could be 2, or it could be 10, or it could be as many as there is. So that's why m is undefined. Oops, I have to change it to m. There you go. Important to understand is that the constraint has to be an equation that's exactly the same as f, except that it has a fixed output. which is what we call a level set. And then the theorem basically states that if f does have a maximum or minimum value at a specific value x sub 0, a specific point x sub 0, then the gradient of f must equal to, here's the important part, a linear combination of the gradient, oh, I missed the gradient here, of all the constraints add together. That's basically what this statement states. I know it does look massive, but that's what it's saying. It's just saying that gradient of f is a linear combination of all the gradient of g, or all the constraints add together. That's all that is. Now, the problem obviously would be, how does that help us find x sub 0? Well, this is how. In order to find x sub 0, which is essentially the critical point of the constraint, or basically meaning the boundary, we need to solve a system of the equation. Now, this is where it gets difficult, because this system of equation in some cases could be a linear system, which we know how to deal with since we learned in chapter 2. The problem is, in some cases, or actually very likely, it's not going to be a linear system, and therefore it actually becomes something extremely hard to do. As a matter of fact, I'm going to say that majority of you have actually never learned how to solve a non-linear system before. So we're going to spend most of the problem that we're going to be doing, the most difficult part will be to solve the system. But what is this system? Well, this system will consist of the following equation. Obviously, the first equation is this one. So that's the equation given by the Lagrange multiplier method. But I did say a system of equation, right? So that means there has to be more. So what more equation are there? Well, remember, x sub 0 must be in the restricted domain of the function, meaning there has to be on the boundary. So therefore, it must satisfy all the constraint also. Otherwise, will not be on the boundary itself. So as you can see, depending on how many constraints there is, this could become an extremely massive system to deal with. And it could be extremely difficult to do. Now, just to show you how to do it, we're going to start our first example by doing the same exact problem that we just did, which we already know the answer of. Let's say we let z equal to f of xy, which is equal to x squared plus y squared. Let x squared plus 2y squared equal to 1 be the constraint to f of xy. Use Lagrange multiplier method to find all the critical points of f with this constraint. So notice this is exactly the problem that we just did, except important to realize is the following, is that this question did not mention about interior of this equation. We're just using this equation as a constraint. The equation doesn't have an inequality. So therefore, in this case, we're actually not looking at interior critical point. We're just looking for the critical point along the boundary, which basically will be critical point on the constraint itself. I always tell my students that when they're doing this type of problem, it's extremely important to make sure you sort it out, the function f versus the constraint g. Some problem it will be listed as such to help you identify them, but in other cases it's probably not. So you have to make sure you understand how to identify this. So how do you identify the constraint versus the function? The function must have a a variable output, must have an output variable, a dependent variable, which in this case we can see that we have z, which is the output variable, equal to x squared plus y squared. So therefore that will be the function, because we don't know what z is. While the constraint must have an equation to have a fixed output at the end, which in this case we see that the equation x squared plus 2y squared is fixed because it's always equal to 1. So this is how we start the problem. We have our function, which is f of xy equal to x squared plus y squared, and we know that the output is z. This is our constraint. This is how our constraint is written. Is g of xy, which is equal to x squared plus 2y squared, and that constraint is always equal to 1. Notice this part right here, the equal to 1 part. That's how you identify that you have a constraint, because it has a fixed output. Remember, all the constraints are literally level set. So now let's try to form our system. Oops. So what is our system? Our system will be this: gradient of f of xy equal to lambda gradient g of xy. That's our first equation now, but here's the tricky part. When I form the gradient of xy, notice the gradient of xy is a vector, which in this case 2x, 2y, lambda. Gradient of g is also a vector. As a matter of fact, this vector is 2x, 4y. This actually would form this. I'm going to go and multiply out the lambda. And since these two vectors are the same, indicate that means that the corresponding coordinate must be the same. We now have 2x equal to 2 lambda x, 2y equal to 4 lambda y. And now we also have our g of xy equal to 1, which is x squared plus y plus 2y squared equal to 1. And that form our system of equation. Important to understand is the following, is that the gradient of f equal to lambda gradient of g would actually generate multiple equations. As a matter of fact, it always generates the same number of equations as the number of independent variable. And then you add on to the constraint. Now, it's always, before we try to solve the system, it's always a good idea to actually think and make sure that our system makes sense. Here we're looking for a critical point, which would hopefully not a finite, not an infinite solution, because I don't think that our function will have infinite critical points, because that would not solve the problem. The problem that we have before is that the boundary has infinite points and we can test all of them. So if it end up having infinite critical point, then we are kind of stuck. So therefore we are expecting this system to kind of generate some finite solution. Because it's non-linear, it could have multiple solutions without being an issue. See, remember, linear system, you'd have one solution, infinite solution, or no solution. But non-linear system can have multiple number of solutions. So therefore, it's not a concern. But it does require the following thing to be true, is that the number of equations involved should match the number of variables. So how many variables is in this system? Because we know there are 3 equations here. And if you count, they're actually x, y, and lambda. So therefore, there are 3 variables here. So therefore, make for a pretty good system, because remember, when you have same number of equation as number of variable, then you have a possibility of having a unique solution, or at least finite solution, compared to infinite solution. Now, this system is definitely a non-linear system because of the x squared and the y squared and the lambda times x and lambda times y. Those are all not allowed in a linear system. So how do we solve this? A non-linear system. So now I want to point out some very common mistake that's to be made. So let's start with this system right here. I'm going to go and try to solve this system. 2x equal to 2 lambda x, 2y equal to 4 lambda y, x squared plus 2y squared equal to 1. Now, as with a lot of other problems, there are multiple ways to solve this system. So I'm just simply presenting the way that I see it. And you might see some different things. However, you do have to pay attention to the following. One very common mistake students make is that they will look at the top equation and say, well, can I just cancel out 2x and just say lambda equal to 1? No. The reason why is no, because you cannot really cancel out a variable. That is probably one of the most common mistakes students make when they're doing this type of problem. You cannot assume that your variable, you can divide by a variable, because your variable could equal to 0 and therefore invalidate the math. So how do you properly solve this system? Well, one way to do that is to do the following. I'm going to take the top equation right here, and I'm going to do this. I'm going to move the 2 lambda x to the other side to get the 0. And then I'm going to factor out 2x. Notice factoring is a different process than dividing, so I can safely factor out 2x without worrying about it. And now, if I look at this, that tells me that 2x equal to 0, or 1 minus lambda equal to 0. Therefore, imply x equal to 0, or lambda equal to 1. Now, here's something interesting, is that this actually is the word or, because it's either one or the other, not and, because they don't have to both be true for the statement 2x times 1 minus lambda to equal to 0. Now, because now I have two scenarios here, I could have x equal to 0 or lambda equal to 1. I can now try to break this into two cases. I'm going to do what we call case 1. We're going to do some kind of case analysis. So let's say we have x equal to 0 to be true. Then what happened is our system of equation, which is normally this, would actually turn into this system. When I plug in 0 for x, my top equation becomes 0 equal to 0. My second equation stay exactly the same. My third equation say 2y squared equal to 1. So now this system is now easier to do, because if I look at the last equation, I can actually find out what y is equal to. So if 2y squared equal to 1, then y squared must equal to 1/2, and therefore y should equal to plus or minus 1 over radical 2, and therefore give us the solution: 2.0, 1 over radical 2, and 0, negative 1 over radical 2. Notice those are the same exact 2 points that we find out when we do the problem the other way. And some of you also might thinking like, okay, so now should I find lambda? The answer is no, actually, I'm not going to find lambda. The reason why? Because lambda is not part of our solution. I'm simply looking for x and y that would form the points for the critical points. Lambda doesn't do anything, and in this case, since I already have my coordinates for my critical point, I'm not going to bother finding lambda. However, in some cases, you might need to find lambda in order to find the point that you need, as in case 2 here, which we know that lambda equal to 1. So what I'm going to do is, once again, I'm going to take my equation and plug in lambda 1 to see what happened. So then my first equation becomes 2x equal to 2x. That is called a trivial equation because it's just basically saying the same thing equal to itself. My second equation becomes 2y equal to 4y. And my last equation becomes x squared plus 2y squared equal to 1. It didn't change. So the top equation, 2x equal to 2x, doesn't do anything. But 2y equal to 4y would tell me that 2y would tell me that y must equal to 0 for this to be true. Because there's no way to satisfy 2y equal to 4y unless y is 0. And if y is 0, then my bottom equation will just become x squared equal to 1. Therefore, x equal to plus or minus 1. And that arrived my third, and fourth critical points. So therefore, this problem has 4 critical points, and we found all of them. And they actually coincide with the same exact critical point that we find out when we're doing the problem this way using parametric representation of the boundary. Extremely important to pay attention to this process of solving a nonlinear system is by identifying some cases that we can break down our system into simpler system and then solve for the solution. Unfortunately, that's all the time I got for today, so I'm going to stop right here for today, and we're going to continue some more on the next video. All right, talk to you guys later. Bye bye.